Uno, dos, tres, cuatro.
Hi everyone, today we're going to take a look at graphing log functions. We'll look at graphing some exponential functions as well. And so graphing logs is really just an extension of everything we've been doing in Pre-Calc 12. So we've done our transformations unit and we've transformed so many different types of functions. So logs and exponents are just another type of function that we're able to transform. Everything here should look super familiar, and I think it's going to be one of the parts that you can say is a real big part of Pre-Calc 12 that makes sense given all of your background. So if you take a look at something in the form of y equals log base 2 of x, and we're choosing base 2 as opposed to base 10 just because if you have a base of 2 for graphing by hand, it's going to be a lot easier than graphing with a base of 10 just because the numbers will be much more contained with a base of 2. Now, doing something like this, if you were to put this into exponential form, you could say that would be equal to 2 to the y would be equal to x. Now, for this statement below, if x equals log base 2 of y, and you put that into exponential form, well, you could say something like 2 to the x equals y. And instead of saying that, I'm actually just going to say y equals 2 to the x, means the exact same thing. Now, think about what we've just said here. Y equals log base 2 of x is definitely the inverse of x equals log base 2 of y. We switched x and y, so these are the inverse of each other. And if x equals log base 2 of y is equal to y equals 2 to the x, then that must mean that y equals log base 2 of x is the inverse of y equals 2 to the x. And we say that right here, and this is a really big statement. Because now we can say that graphing an exponential function is really going to be like graphing the inverse of the log function. And we're going to use that for a bunch of the things that we do today. Okay, so we've already gone over the restrictions, so we don't need to actually go over this much more. But based off of what we said, our base is defined when it's greater than 0. And we said we didn't have a base of 1 because if we had a base of 1, we would have a flat line and it wouldn't be an exponential curve or a logarithmic curve. And given that, if you take a positive base that's not 1 and you raise it to the power of anything, positive or negative, you're going to create something that's going to be a positive outcome. So what we called our argument is going to be positive. That's really the explanation of the restrictions right there. So given that, can we start to answer some of these characteristics? If you have something like y equals log x minus 5, and they want to know what the domain is, you can just think about the fact that x minus 5 is only defined when it's greater than 0. So x would have to be greater than 5. There's no need to have to graph it or understand any concept about it. You just know that that part's only defined when it's greater than 0. We could do the exact same thing for 3x plus 4. And you could easily say then that x is defined when it's greater than negative 4 over 3. Now, part C is definitely a tougher question. So if you think about something like this, this x plus 2 would say that x plus 2 is greater than 0, so x would be greater than negative 2. But there's now an x in our base. And you know that this x subtract 1 is greater than 0 because your base has to be greater than 0. So x would have to be greater than 1. And you also know that x cannot equal the number 2, because if x was the number 2, then you would have a base of 1, and you know when you have a base of 1, it's undefined. So given something like this, what could we do to be able to say what the full restrictions are. You have restrictions over on the left and restrictions over here on the right. How can we put that together? And so the way that I would recommend is I would think about it as being on a number line. If you had a number line and you said x is greater than -2, it's everything to the right of -2. And then you look at your other restrictions and it's saying x is greater than 1. And x cannot equal 2. So at 2, we'd have to put an open circle there. So given like that, you have to satisfy both of these restrictions. And in the region that I'm going to shade in, right here and right here, that's satisfying both the bottom line and the top line, and you need to satisfy both of them. So your restrictions would be when x is greater than 1 and x can't equal 2. You could think about something like if x was 0, that wouldn't be allowed because it would end up getting rejected with one of your situations. Example 2. So if you have the point 25 and it's on the graph of y equals b to the x, what would be on the graph of y equals log base b of x? Well, if you put this into exponential form, you'd say b to the y equals x, and b to the y equals x is the inverse of y equals b to the x. So if your original graph has a point 25, then your inverted graph would be the point 52. Okay, lots of good questions that we can ask from here. Example number 3, determine the inverse of y equals 2 to the x minus 1 plus 3. So we could switch x and y. And probably it should say, well, how much detail do you want us to go into here? Well, they want us to resolve for y. So we still actually have quite a bit that we need to be able to do here. Let's subtract 3 onto the left side. And then from there, let's write this in log form. So let's say log base 2 of x minus 3 equals y subtract 1. So I was just going from exponential form into log form. And we want to isolate for y, so we can add 1 onto the other side. And instead of saying y equals, let's use our inverse notation. And we would say our inverse would be equal to all of this, log base 2 of x minus 3 plus 1. For our next example, if we want to find the inverse of this, step number 1, switch x and y. And then we could add 3 onto the other side. X plus 3 is equal to log base 5 of y plus 1. Let's put it into exponential form. So if we put this into exponential form, we could say 5 to the x plus 3 equals y plus 1. And then we just subtract 1 onto the other side. And our inverse is going to be 5 to the power of x plus 3 subtract 1. Let's put a box around that. Okay, we have a couple questions to be able to practice from that, so give that a try. I would say probably give that a try, but continue watching the lesson and then just make a note that you have to work on these after. Okay, I could let you go loose on these questions right here, and I bet you would be just fine. So if you look at example 4 right here, it says graph this. Now, do we know how to graph y equals 2 to the x? Absolutely. That's an exponential function. And if you just plug in some values for x, like the ones we have in our table of values here, you would come up with something like this. And if we plotted our basic y equals 2 to the x function, let's see what that would look like. Okay, so that's y equals 2 to the x. Now, based off of that, they want us to transform it. And if you look at this right here, what are they saying? They're saying y is going to be equal to 2 to the, well, it says 4 minus x, and 4 minus x is a classic Michelson style question where we need to put it into ready form. We need to factor out a -1, and then that'll create negative bracket x minus 4, subtract 1. So given something like that, what would be our transformations from its original y equals 2 to the x form? Well, let's see. The negative up top here is going to tell us that we definitely have a reflection over the y-axis. And then we're going to go 4 right and 1 down. So take the graph that you have right now, reflect it over the y-axis. And then the graph that you have there, let's move it 4 to the right and 1 down. And I'm just going to bold this right here. This is our final. And I'm going to drop our new asymptote, which is 1 lower than what it was before. And we know it's 1 lower than what it was before because we dropped down by 1 unit. Okay, hopefully that makes sense, and that seems like something that's reasonable. Definitely ask questions in class if that didn't seem good. Okay, a couple more examples. So if you felt good about that first example, you can look at part B, you can look at part C, you can look at, well, let's look at, you can look at part D as well. And I would pause the video and I would give it a try and then just see how you can do with these different types of transformations. So I'm going to go through these fairly quickly just because we've done so many transformations and we went to a decent amount of detail in that last example. Part B is a little bit different because you have a base of 3. So if you have a base of 3, then you could think about what would happen if you sub in these values. You get 1, 3, 9, this would be crazy, 27. Let's not even be worried about that because those numbers are going to be too big, and 1/3. So something with a base of 3 is just going to go up more aggressively. Okay, the negative here means that we're going to reflect it over the x-axis, and then we're going to go 1 to the right and 1 up. Okay, so let's reflect it. And then we're going to take that and we're going to move it 1 to the right and 1 up. There's our new asymptote. And this would be our final graph right there. Okay, part C. So now, let's see, we are graphing and they're going to ask us about some characteristics about this after. Again, if you see something with a 2 and now you don't have a table of values, you have to think on your toes a little bit more. And you have to know that your first step is going to be to graph y equals 2 to the x. Graph your basic function, and then after that, you want to apply your rect to this. So let's graph y equals 2 to the x. Whoops. Okay, so here's y equals 2 to the x. Whoops. Okay, now from here, it looks like we have a vertical compression by a factor of 1/4. We're going 3 right and we're going 5 down. So vertical compression by 1/4 means we're going to take this point here, we're going to drop it to 1/4 of what its value is. So it's going to be worth only 2. It's going to be worth 1/4, and so on. and you would get something that would look like that. Okay, so we've squished it down by a quarter. Then you're going to move 3 to the right and 5 down. Okay, so let's see, we have this point here, this point here, this point here, 3 to the right. 1, 2, 3. Okay, and you would get something that's going to look like this. And if we drop down 5, our asymptote is now going to be down here at y equals -5. So let's see the things that we could answer fairly quickly. I'm going to save the x and y intercepts for the end, but we know our asymptote is going to be y equals -5. Our domain is all real numbers. We're going to go forever to the left and forever to the right. There's no number that we can't put in for x. We can put in any real number that we want. And the range is limited to being above 5. It can't equal 5, so it's just greater than 5. And then for the x-intercept and y-intercept, well, let's see what we have here. So for the x-intercept, I'm just going to do this down here. We could put in 0 for y. You could say 0 equals 1/4. And let's add 5 onto the other side. And then let's times both sides by 4 to get rid of that quarter. So 20 is going to be equal to 2x minus 3. 2 to the power of x minus 3. So if you have something like that and you want to be able to solve for x, well, x is now one of your exponents. And so probably the easiest way to do this is, well, you could log both sides, but I think the easiest way to be able to do this would be to put it into log form. And so if you did that, you could say log base 2 of 20 equals x subtract 3. Let's add 3, and we have x isolated. So your x-intercept, as weird as this is, and then we're using this without a calculator, would be something like that. Log base 2 of 20 plus 3 and comma 0. That's your x-intercept right there. Definitely a really strange question, but I would say if you're struggling to figure out how to get every half mark, that would be the type of question where that's a bit of a differentiator. Now, to find the y-intercept for it, you can just put in 0 for x. And if you put in 0 for x, well, what would happen? You would get y equals 1/4 2 to the 0 minus 3 subtract 5. And that would equal 1/4 times 2 to the -3, which is 1/8 subtract 5. And then you get something that's going to say y equals, let's give it a little more space here, y equals 1/32 subtract 5. And let's get a common denominator of 32. 32 times 5 is 160. So y is going to equal -159/32. I'm pretty sure. You guys can call me out on my math if that didn't go well. So the y-intercept is going to be -159/32. If I was to try to estimate anything with that, try and think of what that would look like, that would be times 5, so it would be almost -5, but not quite. If it was -5, it'd be at -1. Yeah, that is definitely right. It's right, barely above -5. So that seems pretty good. Okay, so the x and y intercepts, I think you'll find a bit of a challenge, but the rest of that should seem okay. Okay, our last log graph to be able to, exponential graph here to be able to look at something with this. Well, what would happen if you have a 2 there? You need to put this into ready form. So we're going to say y equals 2 to the factor of the 2 at the top, and then be 2 to the power of 2x minus 3. And once again, graph your basic y equals 2 to the x function. Okay, and then from here, that 2 next to it means we have a horizontal compression by a factor of a half. And then we're going to go right 3 and 1 down. Okay, so if you horizontally compress this by a half, then that would be right here. This would be right here. This would be right here. And then from there, you want to move it 3 to the right and 1 down. Okay, so our new asymptote is going to be down here, and we're going to be something like this. So in terms of what you might be asked for, you might have to make sure that 3 or 4 points are very clear on your graph, and then you can answer these characteristics on the side here, where hopefully you're finding out now that the domain of all of these exponential graphs are going to be all real numbers. The range is limited to whatever this y value is back here. So as long as there's no reflection over the x-axis, it's just going to be greater than whatever that value is. And if there was a reflection over the x-axis, then it'd be everything below there. In terms of the x-intercepts, you can actually see it. It's at 3. It's right there. Now, if you subbed in 0 for y and you did the algebra around it, that would work out to 3. Feel free to work that out, but that's going to be just fine. The y-intercept, let's save that for last. The asymptotes can be at y equals -1. The y-intercept, if you put in 0 for x, you're going to get y equals 2 to the -6 subtract 1. So you're going to get y equals 1 over 64 subtract 1. And you would end up getting something that would be y equals -63 over 64. And whoops. Looking at that, that looks pretty bang on. It'd be just below -1 right there. Or just above -1, sorry. Okay. Hey, I want to just pause, and actually before we go on to looking at logs, I want to go back to the previous example. If you look back up here, if you want to ask a really not high-end question, it is a high-end question, but if you want to ask something that's sort of a bit of an interesting way of thinking about it, is the way that we transform this graph. We said there was a vertical compression by a factor of 1/4. But there's a second way of thinking about this, and this is just kind of weird. So treat this sort of as bonus. If you had that 1/4 there, you could always say it's like y equals 2 to the -2. That's the same as saying 1/4 times 2 to the x minus 3 minus 5. And your 2's that are the powers have the same base, so you could actually add these exponents together, because they're being multiplied by each other. And if you do that, you could get y equals 2 to the power of x subtract 5. And that's just by joining the -2 and the -3. And this graph right here would be identical to this graph right here. So in other words, vertically compressing an exponential function with a base of 2 by 1/4, if you vertically compress it by 1/4, it would be the same as shifting it 2 units to the right, because 2 to the -2 is the same as saying 1/4. And that's really, really interesting. So if you had graphed this new function here, you would get the exact same end result. You could actually almost look at it as being some sort of, say you had the point 1, 1 right here. If you go 5 to the right and 5 down, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, you will be right there. Pretty cool, I know. Okay, well, let's see what we have here. Whoa. So the next part is this. I almost treat this as a part one, part two. We're going to put all of this together as a part one. I'm going to do a practice quiz as a part two. But we've just spent the last 20 plus minutes looking at how to be able to graph exponential functions. We're now going to graph log functions. And to graph log functions, I want you to think about this. We proved earlier at the very start that y equals 2 to the x and y equals log base 2 of x are the inverse of each other. And so if that's the case, if we know how to graph y equals 2 to the x, we now also know how to graph y equals log base 2 of x, because we just have to take our y equals 2 to the x points and invert them, and we would create y equals log base 2 of x. So we could easily make a table of values just by rewriting the table of values with our x's and y's swapped. So for instance, you could say 1/8 and -3. I'll just fill this in really quickly. 2, 3, and then we'll get 1/4, 1/2, 1, and then 2, 4, 8. Okay, so can you plot our new points? Can we figure out what the inverse would look like? And you'll probably be a little bit slow at first trying to figure out what this shape looks like, but pretty quickly, if you've done this a few times, you can get pretty good at it. And we get something like that. Okay, so this is the graph of y equals log base 2 of x. And let's predict where you would have an asymptote. If your exponential function had the asymptote at y equals 0, well, guess what? You're going to have an asymptote here at x equals 0. And right there, that would be our basic graph of y equals log base 2 of x. And I bet you could predict what our next few examples are going to be. We're going to take that graph and guess what? We're going to move it around and answer some questions about the domain and range and x-intercept and y-intercept and asymptotes. So if you feel good about that, I bet you could probably move ahead and practice these next three. So give it a try, and you can pause the video. Otherwise, let's see what we can do with these graphs here. Okay, so like any of our steps, the first step that you want to be able to do is you want to be able to just graph your basic y equals log base 2 of x function, and then you want to be able to apply your rect from there. Now, graphing y equals log base 2 of x is not that easy. You can refer back to the previous example, or you could always just graph y equals 2 to the x and then invert your points. But I'm guessing that's something that's not going to happen super naturally. So you might want to be able to refer back to it a few times just to be able to figure out what that basic function is going to look like. Here's our original asymptote. Okay, if you're trying to figure out where these points are coming from too, you could, like, let's pick this point here. This is the coordinate 8, 3. And you know that for log base 2 of x, if you put in an 8 right here, that equals 3. And if you put in a 4 right here, that equals 2. And if you put in 2 here, that equals 1. So hopefully that makes sense just in terms of how your substitution works. It's not just seeing it as an inverse, but you're able to calculate the logs of them as well. Okay, so can you do this? Could you reflect this over the x-axis? And then can you go 1 to the left? Okay, so if you look at your original graph here, if we reflect that over the x-axis and we go upside down, you get something like that. And we're going to go 1 to the left. And this is our final graph. Okay, let's see if we could answer these characteristics. So the domain is everything where x is going to be greater than -1. Our range is now going to be all real numbers. And in fact, that's going to be true for all log graphs. It's always going to be all real numbers. Let's leave the x and y intercepts for, actually, you know what? Let's do them this time right away, because this one's your gimme one. It goes through the origin. It goes through 0, 0. So you have an x-intercept at 0, 0 and a y-intercept at 0, 0. And you have an asymptote at x equals -1. Okay, fairly straightforward first question. We're lucky that went through 0, 0, but don't worry, you'll have some questions that are going to challenge you a whole lot more coming up here. Okay, I'm looking at this and I see that 2 minus x and it looks backwards. So let's factor this out. And you could say y equals 3 log base 2 of -x subtract 2. And like any first thing to do, we need to put it into its basic form and graph y equals log base 2 of x. So you have that, and then from here, let's apply our transformations. So our transformations would be, we have a vertical expansion by a factor of 3. We have a reflection over the y-axis, and we're going 2 units to the right. In terms of our rect, let's do our reflection first. So let's put these points in here. Whoops. Okay, so we've reflected it. Let's vertically expand it by a factor of 3. Oh, let's do that here. And then let's move it 2 units to the right. Okay, so you would have an asymptote right here at x equals 2. This is our final graph. And let's see what we can say about the characteristics of it. Okay, the domain. Well, its x is everything less than 2. The range is all real numbers. Our asymptote, let's do that next, is going to be at x equals 2. Our x-intercept, let's see, our x-intercept looks like it's pretty clean. Looks like it's right at that point 1, 0 right there. And it looks like our y-intercept is pretty clean at that point 0, 3. You know what? You could do the algebra and you could take a look at it, but it checks out where that's going to be your x-intercept, that's going to be your y-intercept. So I know I haven't spent a ton of time of talking about x and y-intercepts for logs, but let's spend a little more time on this final example where it's something that maybe isn't so obvious. Okay, you're in luck. We have another example. I promise after graphing this, then we don't have too much more to go. We just have a couple questions right here. Okay, so once again, it's not in ready form. So if we put it in ready form, we get something like this. Let's graph our basic log function. We have a base of 2. Does it always have to be a base of 2? No, but could you imagine if it was something much more than a base of 2? That'd be pretty hard to be able to put on a 10 by 10 grid, and we'd have to really change the way we go about seeing this. Okay, so from here, I would say it's for sure being reflected over the x-axis. We have a negative in front of there. We have a vertical expansion by a factor of 2. We have horizontal compression by 1/2. We're going 4 left and we're going 8 up. So we have a whole lot of stuff happening here. Okay, so here's our function. Let's reflect it over the x-axis to begin with. Okay, from there, let's vertically expand it by a factor of 2. Okay, then let's horizontally compress that by half. Oh man, this is a lot of stuff here. So these x values are going to get halved. And then from here, yuck, we need to go 4 left and 8 up. Okay, so if we go 4 left and 8 up, 1, 2, 3, 4. Oops. 1, 2, wait, right here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So here's our final graph. Whew. Let's put in asymptote right here at x equals -4. And let's see what we come up with. Okay, we'll spend more time on the x and y intercepts as promised. Our domain is x is everything greater than -4. Our range is all real numbers. We have an asymptote at -4. And then we have to look at our x and y intercepts. Okay, so for the x and y intercepts, okay, well, let's see. I mean, I'm pretty sure it looks like that we have a y-intercept there of 2, but let's confirm this. So for the y-intercept, you could put in 0 for x. And if you put in 0 for x, you'd be left with an 8 in that bracket. And that's going to give you y equals -2 times 3 plus 8, which is going to give you +2. So y-intercept of 2, and then the x-intercept. Okay, so for the x-intercept, we could put in 0 for y, and you get 0 equals -2 log. You know what? I'm going to do this. I'm going to do this over here. I'll do it right here where there's a little more room. 0 equals -2 log base 2 of 2x plus 8 plus 8. Okay, so let's subtract 8 onto the other side, and let's divide it by 2 as well. -2, I mean. And so if we do that, we would get +4 equals log base 2 of 2x plus 8. Let's put that into exponential form. 2 to the power of 4 equals 2x plus 8. 16 equals 2x plus 8. And then if we solve for x, I get a pretty nice answer here. X will just be 4. Whew. If we follow that down there, I could see that starting to happen, but I wouldn't be super confident unless we had those points in a little bit and a little bit more detail. And that's our x-intercept. Okay, last 5 minutes here, I promise. Let's just do a quick summary of how to be able to find these. So if you notice, the part I's are all exponential questions, the II's are all log questions. So let's do all of the part I's, and then after, let's do all of the II's. So there's a lot of shortcuts where if you have to answer the quick and easies, you should be able to. So the asymptote for this first question right here, well, you know, all basic exponential functions look like this. So you're just moving up and down. So this is going to give you an asymptote of y equals -5. You would drop down 5 from your asymptote of y equals 0. What would be the x-intercept? This is a trick question. if you have something here, it looks like you're shifting up 1, but you're already above the x-axis, so you're always going to be above the x-axis, so there is no x-intercept right there. If you had put in 0 for y and you tried to solve for it, no, sorry, if you'd put in 0, yeah, if you'd put in 0 for y and you tried to solve for this here, you would get something where you'd have negative 1/3 equals 4 to the x. You would put it in log form, and you would say log base 4 of negative 1/3 equals x. And you would have a negative argument, and you're not allowed to have a negative argument, so you know that there would be no answer because that makes no sense at all. The domain of all exponential graphs is all real numbers. The range, well, the range, let's see, it kind of depends. I mean, your range is usually greater than 0. This negative in front of the x means we're reflecting it over the y-axis, but that wouldn't affect anything with our range, and we didn't shift up or down, so our asymptote is still at the line y equals 0, so y is greater than 0, and that still exists. And then the y-intercept, of this, you could put in 0 for x, and you get y equals negative 2 to the power of 0, and that's equal to negative 1, so your y-intercept there would be negative 1. I know I did that pretty quickly. Okay, well, let's take a look at some of these log questions right here. Okay, for our log questions, if you want to find out the asymptotes, well, that would be at x equals negative 3. That's where this guy here would be beginning to be undefined. The x-intercept, you could put in 0 for y. And you could put that into exponential form. 5 to the 0 equals 2x plus 3. So subtract 3 onto the other side. Actually, let's first say 1 equals 2x plus 3. Subtract 3 onto the other side. Negative 2 equals 2x. And negative 1 would equal x. Okay. Determine the domain of this log. We know that right here. We know that this is going to be something in which 2x plus 6 has to be greater than 0. So 2x has to be greater than negative 6. So x has to be greater than negative 3. Okay. And so then, let's see. Determine the range. Well, the range of a log function is always all real numbers because it's the inverse of a domain and of an exponential function. And so if that's all real numbers, this has to be all real numbers. Find the y-intercept. You can find the y-intercept by putting in 0 for x. And then you'd be left with something like that. So what's log base 3 of root 3? That would just be like saying 1/2. So 1/2 subtract 1. So y equals negative 1/2. That would be your range right there. Okay, lots and lots and lots of info. I totally get that. So let's give you a chance to be able to do some practice. You have these questions as well as the questions from before, partway through the lesson. The review sheet we're going to assign, but you can wait for that in class, and you'll see a second video on that. But that's good for now. So thanks so much.